Welcome back. Today is October the 2nd, and we are now finishing up all the touches here for chapter 6. One thing I wanted to draw your attention here on the halohydrin reaction. The halohydrin reaction works the same as the halogenation reaction. I forgot one little detail here, and that was that when I do this attack here, I forgot one arrow. Let me get the black marker. So when I do this attack, I'm gonna do it like this. I'm gonna do this attacks here, and then this bromine gets kicked off. We have that. I forgot this lone pair coming back up here. This is what I call the double slap. So the double bond attacks the bromine, but the bromine snapping back to form this bond right here. All right.
Does that happen because the bromine has lone pairs?
Yes, exactly right. That happens because the bromine has lone pair. And I don't know if you heard on my videos, I refer to this as the double slap. It's a term that I came up with. It's not in the literature. So, but this is how I explain to myself this. This is like two people fighting, you know, one smacks the other one on the face, and the other one smacks the other one back. That's exactly what is happening here, a double slap. All right, and so please take notes of that. That is similar to this one here. This is also a double slap. All right. And so for the double slap, the return of the electrons usually go to the most substituted carbon right here, this guy. That's your most substituted carbon. Here, this will be your most substituted carbon also. All right. Okay. So that's a little recall that I wanted to do today that I somehow it slipped my mind on this mechanism, but not on the previous one. All right. And chapter 6, let's take a walk on chapter 6 real quick. Let's take a look at the mechanism we have. I haven't counted them, but you're supposed to know them all. So here's hydrohalogenation. Let's see, that's the mechanism for hydrohalogenation. For hydrohalogenation, you do get carbocation rearrangements. That's the hydrohalogenation. I spent a lot of time here. And then we went to the next one is hydration. With hydration, you do get carbocation rearrangements also. Let's see. So very similar. Those two are similar. For the hydrohalogenation, you have an H and a halogen. For hydration, you have an H and the OH that is being added to the double bond. And they both go through rearrangements of carbocations. Here's the mechanism for that. So that's two mechanisms that you should know. Hydroboration. I don't expect you to know the mechanism for hydroboration. Usually we studied this for advanced OCHEM. You guys are starting OCHEM, so I cannot expect you to know this. However, I do expect you to know the reagents that you need, the final product that you make, with that oxygen being always in the least substituted carbon. This one always goes to the least substituted carbon. And let's see. Yeah, and also know possibly the reactant. All right, so that's hydroboration. So far we have two mechanisms that we have to learn. Notice that here I give the importance of the difference between hydroboration versus hydration. Starting from the same starting material, you get two different products, and these are major products in the reaction right here, these two. Where for the hydroboration, the OH always goes to the least substituted carbon, and for hydration, it goes to the most substituted carbon. The H that went here, this H came from the hydride on the the borane, and the H that went here, that is now here, this guy came from the acid. So those are things that you need to start thinking about. One is anti-Markovnikov. It's anti-Markovnikov because the OH doesn't go to the most substituted carbon, and this one is Markovnikov because Markovnikov say, hey, this OH goes to the most substituted carbon. So that's what that means. All right. All right, what else we have? Then these are examples of hydroboration, hydroboration, hydroboration. And then we get, let's go back to hydroboration for a second. The reason for the hydroboration being the way it acts is because it's stereospecific. It's a syn addition, and notice that your nucleophile is your hydride. This is your nucleophile. So your hydride is gonna go where the OH will go in the hydration, to the most substituted carbon right there. And that's because your boron, this guy here, is the most electrophilic of the two. So you have a hydride, which is nucleophile and a base, and you have boron, which is your E plus, is the most electron deficient one. So this one will be your electron negative. So that's how you need to start thinking about this. Boron is acting like a big proton there, so it goes to the least substituted carbon. All right. You can take notes or watch this video again. I just want to keep my slides clean. Then the third mechanism that we learned was the oxymercuration, demercuration of alkenes. This one also this is a double slap mechanism. So this is the beginning of what I call the double slap mechanisms. And this undergoes a SN2 borderline, where is partially SN2. We're going to learn the SN2 in chapter 9, and partially SN1. So I will give more details on that later. But want to introduce the terms now. Let's see. Oh, here's your double slap mechanism. See that? The double bond that is here, this is represented by the double bond, the pi electrons. This one right here actually is that one, and this one is your double bond, and this is the anti-bonding. These ones are your anti-bondings, but they're still there. So the attack could happen from the top or from the bottom. And so notice that that the double bond attacks the mercury right here, attacks the mercury, and then the mercury swings back its electrons and attacks the most substituted carbon. All right, that is your double slap mechanism. All right. All right. So yeah, so we learned this mechanism in detail. You should know this. That's number 3. Here's a comparison now of oxymercuration versus hydration. Notice that on oxymercuration, there is no carbocation rearrangement. It's fixed because of the intermediate. This intermediate here, or this one, they lock the configuration so the carbocation doesn't migrate. It just stays there. Those are your lock reaction intermediates. This one. Notice that now that your nucleophile, whether if it's OH minus, oh no, OH minus, it will be, if it's an alcohol or if it's water, it will go and attack here, and now you will have the OH there after, see right here, after you deprotonate. And so notice sometimes you'll see this minus proton. That is a way of saying, hey, after I attack with water, I have to lose a proton, and usually with water, to get the free OH group. So that is the same thing as you getting this right here, and then another molecule of water comes and grabs it to neutralize it and to get to here. Same exact thing. All right, so that's 3 mechanisms that you need to know. Let me delete this. Let's continue with our walk here through chapter 6. All right, and so here, this slides compares now your oxymercuration with hydration, and you see that for oxymercuration you get a secondary alcohol that is fixed, no carbocation rearrangement. Whereas for hydration you get a tertiary. This is a tertiary, this is a secondary. Came from a secondary carbocation, this came from a tertiary carbocation. There is rearrangement here. And so that's what I want you to be aware of. Now you have an OH that is on the tertiary carbon. All right. Okay, so I think Zoom made my slide go on timeout. There you go. Okay, let's continue our walk here. Then we have halogenation. Halogenation acts just like halohydrin. Both of the first steps are the same. This will produce the double slap mechanisms. Here's your double slap. Double bond attacks the one halogen. This one here. Then it kicks off the other halogen, and then now when it does that, the bromine or the halogen has 6 electrons, and it swings one down. And keep a track of your electrons. So this is the double slap. Here's where it's coming back. It ends up with one charge and 2 electrons right here after the double slap. So you count your electrons. You start with 8 electrons around the halogen that is being attacked. 2 electrons from the double bond attacks the halogen. It breaks off one of the halogens, and then now it has 6 electrons. Then two of those 6 electrons slap it back and return the favor to the alkene. And it goes one slap, and then go second slap, forms the trimember ring. Bromonium or chloronium ion intermediate. All right, so that's how that one goes. Double slap right there. So that's 4 mechanisms. So here are more examples of that. Again, the halogenation and the halohydrin reactions are very, very similar. The reason why they're different is because here we have an inert solvent, and so this is not a nucleophile. In the halohydrin, you have the same components. You have bromine, liquid bromine, or you have chlorine gas in the presence of water, and so the halohydrin that now has a solvent that is a nucleophile, and that's the one that reacts. Here, it allows for the counter ion to attack. It comes back and swings in the anti-position, opposite to where this wedge bond is. So if this is wedge, this next bromine will be dash. It's gonna come from the bottom. It's gonna push this hydrogen. Is gonna move up, and it's going to be placed down. All right. So let's see that. It's right here. Here's your bromonium ion. Now the bromine has 2 choices. In this case, this molecule is symmetrical. You get the you're gonna get let's see, enantiomers. You can do A or B attack, but it comes from the opposite side of the bromine. So be careful when we do the milestone to assign the bromine in the proper position. So like if I am let's see, how do I state this right? Let me think for a second. I will ask a question about this. Yeah, so this will be kind of rough, but I would say I will have 4 different structures like this for something symmetrical like that, and I'll give you 2 fake ones, 2 that are bad. So I will probably give you something like both up. I've done this before. Or both down, which is the same thing, just flip it. You cancel that, and let's say this is A, B, C, and D. The answer should be, so for example, I say answer A is A, answer B, C, and then, or I can do this. Usually I do this when I see duality. I put this. So please take notes. A, B, C. So my answers A, B, and C, and D. I can say A and B. That's wrong. B by itself, C by itself, and I say B and C. So the answer is D, right? Because B and C are the possible products for this reaction because of the anti-attack. All right, so sort of like that. You have to be very careful at analyzing your intermediate. Do not try to solve problems on the next milestone with your eyes only. That only works for James Bond. All right. But for you, you gotta draw. You gotta draw and analyze, and know what you're doing. All right. Okay, that's a little advice there. Let's see, halogenation. Let's see. So we got 4 mechanisms so far. Halohydrin is number 5. Very similar. We already went through an example. In halohydrin, the only variation of halohydrin here is that you can have water as your solvent, or you can have an alcohol. So if you have an alcohol, if you have water, it ends up with the OH. If you have an alcohol, you're going to end up with the R group here, and the R group could be any amounts of carbon. It could be methanol, ethanol, isopropanol. So it'll be the carbon chain of those alcohols. So this is mechanism number 5. Also a double slab. Here's your double slab. And we went through that. What else we have here? Yeah, these are more halohydrins. Halohydrins are also cool to make epoxides or oxiranes. Notice that this was the original, how they made these things. The first type of reactions that were made were like that. And because you have on a halohydrin, you have a nucleophile and an electrophile together. And so if the molecule can, it will make a cyclic molecule. And so this epoxides is what you use when you go to Home Depot and you buy like one of those glues that you have to mix one thing with the other one. So guess what? They call it epoxides, right? Because they have epoxides in one tube. Is the epoxide. In another tube, this is real life application. So when you put a drop of this right there, that is your epoxide. And then you put a little drop of something that's gonna make the glue happening. Let's see, I'm gonna do yellow. So this one comes, and then you put 1 drop of this one here, and you mix them together, right? Like that. You mix it together. Now you have your glue. Your glue might turn color. Let's say your glue became gray. Now you have your glue ready. What you added was a nucleophile. This nucleophile, let's say you added something that had a charge. So let's say you added this. So what this nucleophile did was it came and it pops this charge comes and attacks here and opens up this oxirane ring, and now you have, and this is a polymer, so you have several So you start with something like this, and so you have change of this, things like that. Let's say you have this. When you added your nucleophile, what you have is a nucleophile attacks here and attacks here, and now you have something that looks like this. And this is your glue. All right, because these tri-member rings, they want to open up badly. All right, and that is why you get a really excellent glue with epoxides. All right, that's the chemistry behind that. All right. I'm gonna delete this. Oh, my artwork is gone. Just in my hope to keep my slides clean. All right. All right, so yeah, and there is an awesome mechanism for epoxidation coming right up. This is one of the coolest mechanisms ever, and I went through kind of detailed. Unfortunately, on my video, I think I stood up and went to the board and pointed out. So I want to go over this with you. All right. So here's our double slab. Notice the double slab mechanism is right there here. Double slab. This is the mechanism number 6 that you need to know. So here you have the double bond attacking this oxygen. This oxygen established to be partially plus. I think on my video I did that right. And I started off from this oxygen. I know that oxygen is the most electronegative oxygen in the whole series there because it's attached to a carbon and it's from a carbonyl. So that's partially negative. I go, we're gonna make a battery. Partially negative, partially plus. Then if this is partially plus, this next oxygen should be partially negative. Then finally, this oxygen that is here should be partially plus. So you go minus, plus, like that. And that's why we found our electrophile. This guy is my electrophile. In this whole synthesis, my quest is to find the electrophile that is hidden in here, or make the electrophile. In most of these cases, we haven't had to make the electrophile. When we do next year, next semester, we'll do electrophilic reaction. We have to make electrophiles. Right now, we're not making it. We're just finding where it is. And so this reaction starts off here, attacks the electrophile. The double bond attacks the electrophile. Then these electrons, they kicked off. So this bond breaks. That bond has to break. And when it breaks, these two electrons are going to be forming this double bond here. All right. So those go there. And right away, because you're forming a double bond here, this has to break. And then this guy grabs this H. When this H is free from this oxygen that is plus here, this one, then the double slap takes place. These two electrons in yellow are free to swing back. All right, so make sure you understand this electronic flow. It's beautiful. It's one of the coolest things happening. Check out what happens here. We made the double bond here. Notice that it's color coded with the electrons that were purple. These electrons that are purple right here are now here. Let me make this smaller. right there. And the blue electrons, this one's grab this H, so they're right there. The yellow electrons, these ones, are here. And your green electrons, this guy and this guy, are here, forming the new bond, the one that was from the alkene. The oxygen that is partially plus has been drawn here in blue, but shouldn't be blue. It was actually black. But anyway, it has its 4 electrons on it. And here's your epoxide. You made an epoxide. An epoxide is an tri-member ring with an oxygen on it. 2 carbons, 1 oxygen. That is an epoxide or oxyrane. Those are the 2 names for that. So this is mechanism number what? 6. And so notice that for epoxidation, you can have top and bottom attack. So expect enantiomers. If you have one methyl group that makes it, in this case, if you have a group attached to the alkene, it will not be symmetrical. If you have symmetry, you only get one product. Like in this case, if it's up or down, it will be the same thing. But if you have one group attached to the alkene, then you will have enantiomers, because this guy and this guy are different. Notice that the methyl group is up here, down here, and the epoxide is up, or you can have the methyl up and the epoxide down. All right. So that's 6 mechanisms. Also, this is a double slap mechanism. This is dihydroxylation. It will be on the exam, even though I didn't practice it. This is very useful and usually easy to spot because you make diols. They will be up or down, but in this case symmetrical, so it's the same. But not necessarily when you have something like this. So check this out. Your products, and this is what I was going to say, this is what I will expect to ask you a question. So if you form more than one, the answer should be the ones that are formed. So in this case it's A and C. So I will give you a series of choices like that. 3 will be wrong. Only 1 will be right. In this case it's C, because you form, this is top attack, bottom attack. You have a methyl group that makes the difference. And that is something to account for. So that's mechanism number 7. Permanganate is just like it. It's just like dihydroxylation. You just have to make sure you know the conditions for permanganate. If it's cold, if the reactions are cold, stops at the diol. If the reactions are hot, or if you add heat, then it further goes and splits it. It makes a dicarboxylic acid. Watch out for those transformations. It's a lot to hold on to, but you have to overcome, and you have to write down your name reaction. So put these things on your name reaction. I'll put 2 of them. All right, I'll put both of them. Let's see. Ozonolysis. I absolutely love ozonolysis. As you can see, why? This is one of the coolest reactions where the ozone is going to be broken down from ozone 3 to like maybe oxygen. Not even oxygen. No, not even that. The ozone is going to be broken up into pieces because it's going to lose 2 oxygens. And so ozone sees the alkene, and he says, I know you're gonna beat me, I know you're gonna destroy me, but before you destroy me, I'm going to break you also. And that's why I sent you that silly video of Jean-Claude Van Damme, the Bloodsport, because I absolutely love that movie too. That's one of my favorite movies. And here you see that also now it's going to be destroyed, but he's also going to break the alkene before he disappears. And so, and I make the analogy of, like, if you have two fingers and like you make a pistol with your fingers, now put the tip of your two fingers together, and imagine that's a double bond, and break up your hands in half. Break them up. Take your two fingers, separate apart. The tip on the tip of your fingers, like if this were the tip of your fingers, let's say you have two fingers like that. Here's your hand, and you have the other one here, and here's your hand. As you move out, you're going to put an oxygen here and an oxygen here, and that's what's happening here. All right. So you're breaking up, but adding two oxygens at each end of the broken alkene, and you're forming two carboxylic groups, one to the end of the other one. All right. Ozonolysis can be done reductively with dimethyl sulfide, or oxidatively with hydrogen peroxide, H2O2. All right, so I'll give you examples of that. So this is mechanism number 9, I think, in the series. Let's see. Oh, you don't need to know the mechanism for this. So we still are back to 8 mechanisms. But here I want you to know how to get the final product. All right, and here's the two examples. Notice what you get. So if you break up evenly here, if it's reductive, it's cool because it stays. So here, if I break this in half, and the double bonds are my two fingers from both of my hands, and I open them up, now I'm making a ketone and an aldehyde, and it stays because it's reductive. If my workup, my second step is with hydrogen peroxide, I'm going to insert an oxygen on an aldehyde. But if you have two ketones, they stay ketones. It'll be just like a reductive mechanism, because you can only put the oxygen insertion on the aldehyde after the breakage. All right. So there's 8 mechanisms. This one is not formally a mechanism. It's a proposed mechanism. Nobody really knows the actual mechanism for catalytic hydrogenation. The only thing that we know of is that it's Zn. It acts on the same side or the same face of the double bond. All right, and I give you examples of that. There are 3 useful reagents, catalysts. One is palladium, the other one is platinum, and also nickel. Rainy nickel, believe it or not, the creator of Rainy nickel, it takes after his last name, Rainy. He came to UTC. So this guy is a hero here in the chemistry department, because he's a UTC graduate. What he did was he went to the industry and he took nickel and found a way to make holes in the nickel metal, And so in those little holes, hydrogen will be deposited, um, as a bubble or something like that. But the nickel will bind to hydrogen, and it will do a much faster hydrogenation than platinum or palladium. The problem with rainy nickel is that it's very reactive and it ignites. And you have solvents and you have hydrogen gas. You pretty much are dealing with a bomb. You have to be careful what you're doing. I remember when I was in the industry, one day I reduced a double bond from 1 kilogram of starting material with rainy nickel. And like 3 days after I finished the reaction, the owner of the company came to me, "Hey, Herman, have you run that rainy nickel reaction?" He just want to give me tips about it. I said, yes, I did it like 3 days ago. He was happy that I finished it, but he didn't want to see me blowing up his company, I guess. So I wasn't planning on. I wanted to keep my fingers too. So yeah, very, very dangerous stuff. So let's see. Then we did alkyne hydrogenations using Lindlar's. Lindlar's it's a triple. It's a reductive agent to go from from triple bonds to double bonds, and it's a syn addition. It puts the two hydrogens on the same side. Then you have a cis kind of alkene. All right. Yeah, you do have a cis. See, this group is here, this group is here. That's cis or Z. And one more double slab mechanism. That's probably number 9. This will be your carbenes. Carbenes are really reactive because they don't have a charge, they're unstable, and the lifetime is short. Anything that is reactive, the lifetime is going to be short because they're going to take the fast lane in life and they're going to crash and burn or something like that. I don't know. But yeah. So here's the double slab. The alkene always attacks first. And because the carbon here is electron deficient, this carbon only has 6 electrons. Count them. 1, 2, 3, 4, 5, and 6. That makes it E+. That's your E+. Here's your E-. And then attacks. Once it gets a full octet, it say, hey, I have a lone pair here. Take it back. And then it makes the double slab. And make an awesome cyclopropane precursors for more detonators. They are highly used in Hollywood. These are the putties, like I said before, the putties that they put in the doors to blow them up. And then they make like a shock wave with some electrical pulse. That's because these bonds are banana boats and they want to break up. So yeah, these bonds are bow. All right, and so I'll go through some sort of syn addition, match or clash. You just have to watch my video for that. Yeah, that's pretty much it. I didn't go through so much here today on our practice homework worksheet. We will be finishing this on Monday. We only have a few examples left. If I had time this weekend, I probably will have some examples. I'll maybe find some more examples or make up some more examples from Monday, but I don't think this will be enough for Monday. So I probably will have a worksheet by Sunday that you can print out. All right, and we'll have more practice. So 9 reaction mechanisms. Some of them are really quick, like this one. Where is it? Like this one, the addition of carbons. That's not bad. And by the way, these are not on the book because the textbook is kind of limited. But I'm not limited to the books, to the textbook. I want you to know as much as I can. So I bring up other sources on my slides, but I stick with mostly with what's on the book. Any questions up to this point? So this was kind of like I was planning on doing this review on Monday, but I've been getting emails asking people ask me how many mechanisms do I need to know, Dr. Odens. I'm like, all of them, because I took the time to teach you all of that. So you gotta know them all. All right, and it's good food for your brain. This is your knowledge right here. All right. Anybody has a question? I'm noticing that my participation in class has been dropped to almost half. I'm supposed to have 73 students in this class, and I only see 35 participants. Oh Lord. I want you back. I want you guys to come back and, study and share class with us. All right, any questions? Any questions up to this point? I'm sure you guys have questions because there's a lot to learn, but should be fun. Shouldn't be a dreadful event. Questions? All right. I'm gonna count until 30. They say like when the professor asks for a question, you need to wait 30 seconds because that help the students that are on the side to just be brave and ask that question that is bothering you. Go ahead. You have 30 seconds. All right. My monologue has ended here, I guess. I wish you guys a wonderful weekend. I'm gonna stop the recording.